going to go ahead and get started. My voice is a little sore, but I'm going to try to sort of talk a little more quietly into the microphone. Okay, so today's announcements. I guess those of you who were at lecture last week, Garrett covered Chapter 4 very competently and well for me. So we're done with Chapter 4 now. So the sapling is due Friday 9 a.m., which means we are now on to Chapter 5, which I posted last week. Also, I'm going to go through the stack of regraded exams today and tomorrow, so I will have those with me at the next lecture if you want to pick them up then, or failing that, I'll just parcel them back out to the recitation TAs after that so you can get them from your TA. If you submitted a regrade, you may see your score change in Canvas if that ends up getting you more points back. Okay, questions about that? Okay, cool. So, Chapter 4, we spent a little while looking at sort of naming and structure of alkenes, and then we got into the first set of actual reactions that we're looking at for OChem. So multi-step in most cases, where we have multiple consecutive steps of arrow pushing mechanisms. Just sort of a quick overview of what we're looking at there is addition reactions of alkenes. So as we get into Chapter 5, we're going to be looking at more alkene reactions. Splitting them up between Chapters 4 and 5 is done a little bit awkwardly in Loudon. Like really it makes more sense as one huge chapter, but then it's a really big chapter. So I guess Loudon opted to cover a couple example reactions up front in Chapter 4, and then Chapter 5 has a lot more along the same lines. Okay, so just as a refresher, the general gist of what we're looking at is we got a couple alkenes, they got a double bond. What we're going to do is add something to that double bond so that each carbon is going to gain a new attachment to an atom. So we could say X, Y here just to keep it real generic on the arrow, but that's not any specific reagent necessarily. That's just we're adding other stuff to this alkene. So each carbon gets one new bond to something else, and as a result, it loses its pi bond to the other carbon. Okay, so these are alkene addition reactions. We're going to see one reaction that goes a little bit further from this and breaks both the pi and the sigma bonds, but that's towards the end of this chapter. Also, as a quick reminder, one thing that's worth mentioning is that none of the reactions that we're covering in Chapters 4 and 5 do anything to aromatic rings. So as a reminder, we consider aromatic rings, even though they have a carbon-carbon double bond, to be a separate functional group from an actual alkene because they react differently. So if we take something like this, where we've got an aromatic ring and an alkene, and we do some kind of reaction like this to it that you should have seen last week. Okay, so I'm going to be adding an H and an OH to each of the two carbons here. Do you guys remember, is this Markovnikov or anti-Markovnikov style? Yeah, it's Markovnikov, right? Because we make a carbocation here on the more substituted carbon. So we end up adding the more substituted, giving the more substituted carbon the group that's not an H. Okay, so that's kind of one thing that we're going to have to focus on here when we start introducing Markovnikov versus anti-Markovnikov style reactions is what adds where. Okay, so we do this reaction. We're adding an OH and an H, but note that it's only changing the alkene. It's not doing anything at all to the aromatic ring. So we're not going to see things that we can do to change this aromatic ring until much later on. For now, pretty much treat this as just some unreactive lump that does nothing. Okay, questions about that? Okay, cool. So the first new reaction that we're going to see in this chapter, like a lot of the stuff in this chapter, the name kind of tells you what it is. So dihalogenation is what we're looking at here. So we're going to be adding 2 halogens to the molecule. Okay, so I'll put a couple quick examples up and then I'll talk about some details. So here's an alkene. We can take, for example, Br2, and just like in this simple alkene example up top here, we're going to get rid of the pi bond and keep the sigma bond between carbons. And to make up for its loss, each carbon gets a new attachment to a bromine atom. So we're adding Br2 overall. Another example on a different alkene. If we add, for example, Cl2, then again we're breaking the pi bond and we're adding a new chlorine atom to each of the 2 carbons there. Okay. So, some interesting and useful things about this reaction. One is that we'll pretty much only ever see it with these 2 halogens. Br2 is actually the easiest to use for this. Does anyone know like what elemental pure bromine looks like if you're dealing with it in the lab? Yeah, I think, yeah. Yeah, it's a dark brown liquid. So it's pretty corrosive, but it's a lot easier to weigh out than chlorine, which is a gas, like a yellowy green gas. So if you're doing this in the lab and you just have to dihalogenate something, bromine's the way to go. So it's liquid at room temperature. So dichlorine, or Cl2, is a gas. It's harder to work with, but you can still like bubble it through the reaction mixture and get it to go. It turns out the other 2 halogens, fluorine and iodine, just don't do this reaction as favorably, just because of the way the thermodynamics work out. So we're not going to see this reaction happen with those 2. Okay. So questions about this so far? Okay, yeah. Oh, sorry, you're just stretching. Okay, so the products that we're making out of this are called Vicinal Dihalides. This means that the 2 halogens are on neighboring carbons. If you know the word in the vicinity of, or like vicinity is kind of the same root word as vicinal. And it makes sense that they're on neighboring carbons because those carbons had to start out being pi bonded to each other as part of the alkene. Okay, so the mechanism that we're going to look at for this reaction actually starts out looking a little bit similar to HX addition, or hydrogen halide addition from chapter 4. So it's got some similarities, but it also has a ton of differences. Okay, so let me actually draw HX addition up here too for comparison. So if we're doing HBr here, then you should remember from last week that the alkene goes out, attacks the proton, kicks out the halogen, and you end up temporarily with a carbocation here, and then a halide leaving group, which can then go and attach onto the carbocation, maybe after some rearrangements occur depending on the molecule. Okay. For dihalogenation, though, something a little different is going to happen. So if we started out with the same arrow pushing, and let's do this on bromine as an example, we could show pretty much the same arrows where the alkene goes out and attacks one of the halogens, and we have just as good a leaving group on this molecule as we did up here. We're still kicking out a Br-. So we could think about why not just go through the same intermediate, make a carbocation here, and kick out that halide leaving group. Right? Looks pretty reasonable. The difference between these two reactions is that up here, the hydrogen that we just added is pretty much powerless to do anything to help. Like, it has no electrons of its own. It's pretty useless. You're just stuck with a carbocation until later on when this comes over and attacks the carbocation. Here, though, that's not the case. That bromine is a lot better off for having lone pairs that it can throw at the molecule. So rather than letting this sit as a carbocation, we could show this swinging over, donating a lone pair, and bonding onto this carbon as well, which would get us to here. And if you go through and count for formal charge, you'll see that after this step, this bromine should have a positive charge. Or you could just figure it out as this bromine was neutral. It gave up electron density by doing this. It should end up holding the positive charge. Okay. So that looks pretty reasonable as a mechanism. It turns out, though, that people sort of observed this experiment very closely and found out this never actually goes through a carbocation at all. Like, if it did, we would expect to see, in the brief instant of time before this happened, we would expect to see potentially carbocation rearrangements depending on how fast they are compared to this ring closing thing. So it turns out this whole thing never actually exists at all. Like, it just bypasses the step that's kind of most analogous to up here and just goes straight over to that three-membered ring. So I'm going to put brackets around this and say, not really part of the mechanism, do not draw. Okay, so we can use that as sort of like a mental guide to like stepping stone us towards what actually happens, which is all three of these arrows, these two over here that are just like the HX addition, and this third one of the ring closing down are all going to happen at once. And I'm going to hop over here. So if we combine these two steps, what we get is so we want the alkene to go out and attack the halogen. We want the halogen to drop its leaving group. And at the same time, we want one of the lone pairs on the halogen to kick around and attack where the carbocation would exist if we ever gave it a chance to form. And so in one step, mechanistically, we are going to hop straight over to this three-membered ring form where the bromine carries the positive charge. Gesundheit. So I guess like another way that you can sort of confirm this to yourself is it's not exactly resonance. Like Loudon is a little hand-wavy on whether they treat it as resonance or not. I think they do use resonance arrows, which is annoying. But between the two possible ways to show the product, one where it's ring open and one where it's ring closed, this form has a full octet on every atom. Like the bromine here with its positive charge still has a full octet. Here, the carbocation does not have a full octet when it's got a positive charge. So it's not exactly an apples to apples comparison, but we would expect like this thing to probably be a little bit more stable just on the basis of everyone's got a full octet. So that's why energy-wise it makes sense to sort of skip the carbocation entirely. Okay, so questions about what's going on there during the first step of the reaction? Yeah?
How do we know that the electrons from one bromine versus the other attack the carbocation form?
Ah, good question. So how do I know like the other bromine doesn't immediately swoop in and attach to the carbocation? Yeah, so I think the best answer to that won't actually come up until a couple chapters from now when we start looking at like stereochemistry and which direction atoms are pointing. But it turns out we have pretty good proof that when this attack happens, the second bromine that adds always has to add from the opposite face of where the first bromine added. And so that's kind of a good verification that if they both added at once, they just stick on whatever direction they're pointing. But if they sort of one adds on first and the other has to sort of come in from the back and kick out the bond. So let me actually show that first and then that might make more sense. Okay, and actually while I'm showing this, this particular intermediate, the three-membered ring that we're drawing here, has a particular name that I'm going to use, and that's for this specific one with bromine, a bromonium ring or bromonium ion. Like a lot of names, IUM at the end of something often indicates a positive charge. So bromine, but with a positive charge is kind of what's named after there. So if it's bromine, it's bromonium. If it's chlorine, it's chloronium, I guess. But the more general form is a halonium for whatever halogen. So halonium in general. But since bromine is going to be the halogen that I use like at least 3/4 of the time for this, I'll probably just call it the bromonium ring. Question?
Does this ring form with all like dihalides?
It does, yes. So chlorine's going to do exactly the same mechanism. Iodine and fluorine, I'm not 100% sure. Fluorine has actually got enough energy at stake that it might just like say, I've got energy to burn, let's make a carbocation, woo. But I'm not 100% sure about that. So, question?
So will all polonium ions be connected to two carbons with sigma bonds, and then they'll each have two lone pairs and a positive one?
Yes, at least all of the positive charged halogens that you'll make during this reaction. I guess if you made positive charged halogens during some other reaction, it might end up looking different, but I'm not sure if it would be called still halonium under those circumstances. Yeah. Okay. All right, so to wrap this reaction up, we've got the bromonium ring here, and it turns out that the bromide ion that we kicked out earlier can at this point come around, attack on there, and I'll explain why I picked that carbon in just a second, and pop the ring back open. So we're kind of reversing the step where we closed the ring down in the first part. Okay. And so we're going to end up with another bromine attached onto this carbon here. Okay, so the reason why I showed it attacking here, so I guess what we're looking at is why attack the more substituted carbon? Why not the less substituted carbon? So really it comes down to charge distribution. There's more of a delta positive at the more substituted carbon. So again, Loudon kind of shows this as resonance, which I'm not 100% on board with, but I guess it's kind of a gray area. Because we are breaking sigma bonds to do this. But we could show sort of the reversal of this ring closing reaction where we could let's use equilibrium arrows. We could conceivably not have the ring here and make a carbocation there instead. Or we could conceivably even go the other way, break the ring open favoring the other carbon. Okay, so out of the 3 different ways we could show this thing, kind of like I said over here, the bromine with a positive charge is the best option because here everything's got a full octet. Out of the other 2 options though, top or bottom, which one looks the best? Top, right? Because it's got the more substituted carbocation. It still sucks compared to everything having a full octet. It's not great, but this one down here is worse. Okay, so whether or not you really want to call this resonance because you're breaking sigma bonds, you can still sort of draw an overall charge distribution of the whole molecule that shows some of the positive charge getting parceled out to the 2 carbons of the ring. So, so the bromine officially has the full positive charge for bookkeeping purposes, but you are going to have a little bit of delta positive on both carbons. And due to its better ability to carry the positive charge, this one here, this more substituted carbon, is going to have a bigger delta positive than this one up here. So, when the molecule's sitting around like this in the bromonium ring form, when the bromide comes around looking for something to attack, I guess it could attack the Br with the plus charge on it, but that wouldn't really do anything productive because you're not actually getting a lone pair, a third lone pair back onto the bromine by doing this. If you want to actually get things back to neutral on all of the atoms, you're going to have to attack a carbon and break a bond towards the bromine to make that happen. So out of the 2 carbons, this one looks like the better attack position for the bromide to go for. Okay. So that's kind of why up here I showed the bromide going in for the more substituted carbon. So for this particular reaction, it doesn't even really matter. You can't tell afterwards like which one was added first and which one was added second. But if we hypothetically used something other than Br minus to come in and do the attack and add second onto the molecules, then we might be able to start to tell maybe what order things added where, and that would make a difference. So that's actually what we're going to look at for the next reaction. But any questions about this one before we move on? Okay, cool. Alrighty, so what we're going to look at next is Halohydrin formation. Okay, so again, the name should help you sort of remember what's going on here. We got a halogen and we got something to do with water. So halohydrin formation. Turns out those are actually exactly the 2 reactions or reagents that we need to show on the arrow here. So we take an alkene and we could, for example, use Br2 in water. And we're going to end up adding whatever halogen to the less substituted carbon and an OH group to the more substituted carbon. Okay, so that's one example. Using the same example alkenes that I did before. Maybe let's do Cl2 and H2O here. And out of the two carbons, the more substituted gets the OH, the less substituted gets chlorine. Okay. So the mechanism is almost identical to what it was for dihalogenation. Just obviously there's going to be a little bit of difference once we start bringing in water. Question?
Where's the other hydrogen go? First one?
Good question. I'll show that as a byproduct. So, okay, so mechanism for this is going to start out just the same. So alkene goes and attacks. We break the halogen-halogen bond and close down the bromonium ring. And that gets us to here. Okay, so this is actually kind of another interesting side point that's worth mentioning, because I do still have Br minus floating around, but unlike before, I also have water molecules, H2Os, floating around. Let me space those out a little bit more just so it's not confusing. Okay, so these two are floating around. So you might be asking, this one's negatively charged. Why doesn't this come in and just finish the reaction same as it did before? Like, why is water doing this? Turns out there's two parts to the answer. One is that there's usually going to be a whole lot more water molecules around than there are Br minuses at any particular point, just because Br minus we can only create through doing the first part of the reaction. Water is just like part of the solvent for this. The other part is that water is actually not that different in terms of its ability to break open the ring here from Br minus, even though the negative charge might make you think like this is better as a nucleophile. It's actually quite stable with its negative charge. It's not really super enthusiastic about going after a carbon. We'll look at nucleophilicity later on, but this doesn't really have much of an advantage of power, and it sure doesn't have an advantage in numbers. You might get a few cases where this will go in and finish the reaction, but most of the time, statistically speaking, water is going to win out. Okay, so water does pretty much the same job that Br minus did in the previous reaction. Attack the more substituted carbon, kick out the bond to the bromonium, and we're not quite done yet because we've attacked with our oxygen, but our oxygen is still trailing both of its hydrogens, and it was neutral before, which means it's got to be positive charged afterwards. So we actually have an H2O plus instead of just an OH neutral group hanging off of here. So we have to do one more thing to finish up this reaction. We've got to deprotonate this, and I don't remember if Garrett covered this or not. I'm not super picky about what you show doing deprotonations, as long as it's something that's not completely unrealistic as far as pKa's. So I'm okay with you showing, for example, what's probably going to be most likely is another water molecule coming in, plucking off that H, getting the oxygen to be neutral, and getting you to the final product. Or you could show a Br minus coming in and doing it. Br minus as the base is less likely, but it does give you a balanced reaction where you're making a molecule of HBr overall. Or I am also okay with you showing no base coming in and doing this, which would actually end up looking like just that bond breaking and the H sort of drifting off into space with no electrons of its own. Question?
Yeah, if you don't show a base, would that be considered the autoionization of water?
Not really, because I guess neutral water does this a lot less easily than something that's already plus charged, which we know because the charge effect means it's way easier to shed a proton. But really, like, this is not something that's really going to happen on its own. It's just a factor that there's several things around that could do this job, and getting bogged down in which one's actually doing it is a little bit sort of pedantic, I guess, for a lot of organic chemists. So ambiguous deprotonation, I guess, is how it's described, is A-okay by me. So you can just show something losing a proton if that is a reasonable mechanistic step and going to here. Or let me go over here. One last option that you might see that I tend not to use, but I think the textbook does once in a while, is not actually show the arrow pushing at all. Let me scoot this out the way. So they might just say minus H plus on the arrow and go to the neutral deprotonated form that way. So there's a bunch of ways of showing it. Most of them have to do with the fact that proton transfer is actually a lot of the time so fast compared to most of the other mechanistic steps that honestly getting too nitpicky about exactly what's doing it, as long as you're not showing something like completely ridiculous, is totally fine. So, question?
So would we be expected to show the bromine ion like hydronium as byproduct?
No, so that's sort of another thing where organic chemists are a little bit more slapdash, is you generally don't have to show balanced equations or reactions. Like, if you're making byproducts, you can show them, or you can just say, like, at some point we spat out a Br minus and then it's never heard from again. That's totally fine and commonplace. So, yep. Okay. So I guess no matter which way you show the deprotonation step at the end, we end up going to sort of this rough analogy to what we did in dihalogenation, where we've got a halogen on one carbon and an OH on the other carbon. And the mechanism is almost the same except for the deprotonation step. It's just at a key point midway through the reaction, bromine or bromide could have come in and attacked, but instead something else that was around came in and did that instead. Okay, so other questions about this? Okay, cool. So I'm going to take a minute and erase the board if you guys want to stretch or whatever. So the next one we're going to cover, pretty much if you've got the previous two down, you've already got this one. It's the same thing yet again. So we're covering three very similar mechanisms here. So this one is haloether formation. Okay, so I'll put the overall reactions up first and then do the mechanisms again. So the only difference between this and halohydrins is instead of water, we're going to use a molecule of alcohol. So we can do Br2, and then instead of H2O, we could use some kind of ROH. And now we're going to end up keeping the OR part of the molecule that sticks onto the more substituted carbon. Another example before I get into details. On this alkene, Cl2 and ROH. Might give you this. Okay, so you'll notice that for both parts of the molecule, and this is actually kind of a useful shift in perspective. So we know that ethers are anything following the pattern of ROR. We've got an OR group in our molecule, and we can actually treat the entire, what used to be our starting material more or less, as another R group. So even though it looks like it's just like our starting molecule with an extra bit hanging off of it, the whole thing that we've made could be classified as an ether. It's got an ether functional group in it now. Same thing here. Our entire starting molecule is another R group. So we've got ROR. Okay. So questions about that so far? Okay, cool. So mechanism, just the same as what we saw over here. You start out attacking the halogen, kicking out a halide leaving group, and attacking back onto the molecule with the other one. That gets us our bromonium ring. And now we're sort of down to a similar choice that we had in the last reaction. We could attack with a Br- that we just kicked out, but given how much more of it there is around, odds are a lot better that an ROH, an alcohol molecule, is going to come in during this step. Okay, so we attack there, kick out the bond to the ring. And just like before, we haven't actually dropped anything off the oxygen yet, so we still have a positive charge that we got to deal with. And it turns out that it's a lot easier to do a proton transfer step a lot of the time, like an acid-base step, than it is to get an R group off of there. So this H is going to come off. So again, you got choices on how to show that, but I'm just going to use another molecule of alcohol, come in and pick that off. Which gets us to there. Okay, so questions about that one? Okay, cool. So this actually, even though it's just about the same mechanism as what we saw over here, this actually opens up one very interesting possibility for us, which is, what if the R group that we're using here is actually part of the same molecule to begin with? Like, what if you have an alkene and an OH group in the same thing? So what we're going to take a quick detour and look at now is intramolecular reactions. So one part of a molecule doing a reaction with another part of a molecule. Okay. So what I'm going to show here is okay, so I'm going to number the carbon. Actually, I'm going to number all the atoms here in the molecule. So I'm going to start with oxygen as 1, and then I got 2, 3 with the methyl, 4 and 5 with nothing, and then 6 and 7 are the alkene. All right, so I'm making a chain with 6 carbons and 1 oxygen atom. What I'm going to do is expose this to bromine. I don't need to add anything else because I already have my ROH as part of the molecule, right? I've got my ROH and I've got my alkene as part of the same chunk. What I'm going to do is, I might actually redraw this down here. A little bit less crowded. Okay, so just like always, alkene attacks, kick out the halogen, close the bromonium ring down, and I start out making a bromonium ring over here. Okay, so at this point, this is where water or whatever ROH molecule might come along and get involved, or my halide, if that's all I have going. But in this case, the OH is already like right there tethered to the molecule, like ready to react. So what's going to happen is, again, it's going to go in for the more substituted carbon. It's going to swing around, attack onto its own tail like that, kick out the ring like always. And here's where numbering is super duper handy because otherwise it's easy to lose track. I know I'm numbering this as 1, 2, 3, 4, 5, 6. You can number it however you want so long as you're consistent. You can just use like smiley faces or stars or whatever, just whatever makes it easier for you to count. But I am making a ring that consists of 6 atoms. First this oxygen and then 5 carbons. So what I'm going to end up with is, so I've got oxygen as 1, and then it loops to 2. 3 has the methyl. 4 and 5 have nothing. 6 just got a new bond to the oxygen, and it also has an attachment to 7, which is not part of the ring. 7 didn't get closed into the loop that just formed. So that gets me to here. Oh, and oxygen still has its H on it. Okay, so that might be a little bit tricky to see at first, but it really is exactly the same arrow pushing as up here. It's just you're doing it from one part of the molecule onto another, so keeping track of what attaches where is sort of the hardest part of this. Okay, and then to finish this up, like always, I just got to deprotonate that. And once I've done that, I'm going to get to here. Question?
This is kind of on the last. So is the oxygen, because wouldn't it be kind of unfavorable for it to have?
It would temporarily, so yeah, it's never going to stay there, but it turns out, I guess if you show the reaction energy diagram, it's sort of like a high valley that it goes through on its way down to like the far side of the reaction where it's getting to something that's more stable overall. So it's not going to hang out here for long. It's just passing through on the way to a more stable product. So yeah, good question though. That is something you should be checking, like are the intermediates that I pass through too unstable to even form? But it turns out if it's got a big enough motivation to do so in the long run, it'll still go through it. Okay. So I guess a few things about intramolecular reactions. One is that if the functional groups that you're reacting are forming a new bond between them, which we know from up here, we're forming a new bond from the alcohol onto the alkene carbons, or one of them anyway. If you do the same thing intramolecularly, you should expect to be forming a ring because these two groups are already tethered together. If you loop them around and attach them again, you're closing a ring down. So that's a really common trait in intramolecular reactions. There's nothing about this specific mechanism that causes it, like any of the mechanisms that we've seen, if you're doing it as a reaction that sticks two different organic molecules together, you can make it a ring-forming reaction if you have them start out as part of the same molecule. One other thing that's worth pointing out on this as a side note is that this reaction actually is made a lot easier by the fact that the OH is already tethered to the far end of the molecule. So this is called the proximity effect. And I think Loudon doesn't cover it for another chapter or two, but I like the analogy that they use in the book where it's sort of like if you're just sent out into a crowded airport and told to find someone, it might take you a really long time. But if you're told, hey, I'm going to tie a rope around your waist and the other end is tied around the person that you're looking for, you're probably going to find them really quickly because they can never get very far away from you. Same thing here. If you're trying to react these two functional groups and they can never get any farther away than like the far ends of the molecule, odds of them wrapping around and bumping into each other are way, way faster or way higher than they would otherwise be. The one possible trade-off that we're going to spend more time looking at later is depending on what size of ring you're forming, that might actually make things more difficult. So it turns out 6 is actually the best size for a ring to be, which is why I chose this particular molecule to do this example on. If you're doing a bad-sized ring like 3 or 4, that might actually make things harder because then it doesn't quite have the flexibility it needs to get its bits together, like the OH and the alkene, to actually stick them together into a ring. Okay, so questions about that? Yeah?
How do we know dihalogenation doesn't happen in this chemical?
So that's a good question. Like there might be some % of the time where dihalogenation would actually happen, but kind of like up here where dihalogenation could happen, but because we have ROH around, that actually ends up dominating sort of the reaction, so haloether formation wins out. Same thing here. If you've got the functional groups around for it, you've got an alcohol and a BR, haloether formation is probably going to win out statistically. So, yep. Okay, so that's a pretty good stopping point. So I'm going to pick up there next lecture.